is related to quantum transport simulation of nano-devices using the non-equilibrium Green's function formulation in MATLAB. So in this project, basically I have just developed MATLAB based quantum transport simulator for the non-scale devices using a non-equilibrium Green's function, okay, formalism. So basically, in the complete simulator nodes, we have just detected that the electron transport within our tight binding framework and the accurately computes energy dependent transmission density of states with the local density of states, and the semi-infinite leads are basically incorporated through the analytical surface Green's function and enabling the realistic open boundary conditions. So the main thing is that in the implementation, basically this implementation generates the physical observations including the conductance, spectra, current energy profiles, along with the scaling studies for the device length and the contact coupling strength as well. So the 8 dependent visualization modules basically present here, in which provides a clear interpretation of resonance, quantum confinement, and the coupling effects as well. So NEGF basically method is used to develop the solution of the quantum kinetic equation, and for the numerical stability basically is ensured via sparse matrix solvers and the controlled energy boarding. So I have written the abstract with the keyword on introduction. In the introduction, I have just added how quantum transport simulation of nano devices using the NEGF formalism in MATLAB. So next one is basically I have just added the energy versus transmissions parameter, which we have used in the MATLAB as well. So in advanced post-processing modules basically generates the conductance spectra and the special energy LDOS map, and enabling the visualization of resonant states as well as the confinement effects as well. So basically the proposed framework is deliberately modular to facilitate extension to higher dimensional materials, multi-terminal geometrics, and self-consistent electrostatic coupling. So here is the background and motivation. In the background and motivation is that the main purpose is that at nanometer scales, electron behavior is fundamentally quantum mechanical, exhibiting wave interference, tunneling, and discrete energy quantizations. Okay, and the computational framework is basically to involve the matrix operations and numerical inversion schemes that must remain stable over the wide energy ranges. So here is a quantum transport of energy, and which basically provide us the transmission of spectrum, total density of states, LDOS map, conductance versus Fermi energy, energy resolved current, and LDOS as well. Okay. Says objective is the same like how we will compute the transmission spectra, density of states, local density of states, like LDOS mean local density of states, and conductance curves as well as the energy resolved current distributions. So here is the numerical stability with the performance of enhancement. Okay. So these are the parameters I have defined, which is basically energy resolved current specie, and the visualization versus physical interpretation is that in the heat map visualization basically depict the confinement included and induced states and standing wave patterns across the device lattice. Model validation and benchmarking basically, which is basically density of states as well as and comparison with the energy. and the local density of states LDOS versus connect with the energy parameters. Okay, next is basically future extensions and research directions. So in the future extension, basically we need to we can extend this to two-dimensional materials, including the graphene and ribbons and transition metal um, diclocognathide ribbons basically. Okay, so the multi-terminal geometrics enabling the non-local transport investigations are also natural extensions of the platform. So the problem statement is here mathematical model. In the mathematical model, I have just added all the equations used in this model, and yes, this one is basically I have just added the Landauer expressions equation, and this one is basically local density of states as well as all the integral formula and methodology is explained here. In the methodology, I have added the conductance versus Fermi energy parameters, and next one is design MATLAB simulation. In the MATLAB simulation, I have added all the leverage matrix operators for the efficient computation for the Green's function and self energies, and energy grid is basically used to transport the properties over the desired spectral range as well. So here is the transmission spectrum output results and the graph of nano devices function of energy and the density of states. Next one is local density of states map, and next one is LDOS energy states along with the Fermi energy. Okay. Here is the energy resolved current distribution, basically contribution as a function of energy transport under the applies, and next one is conductance versus Fermi energy graph. Okay, so here is a transmission for different couplings, and next one is basically transmission versus spectrum for devices of different lengths. So then the discussions basically explained how the total density of energy confirms the presence these days levels, and while the local density energies map basically illustrates how electrons are spatially distributed across the device, highlighting the localized and delocalized states. Okay, so next one is conclusion and references are added. Let me just show you the output results. These are the output. You just open the quantum transport simulation, and you just open this, and you will when you will run it, and you will get the output results accordingly. These are the parameters. Milton, all the plots are distributed in terms of MATLAB code. Functions are defined surface function at the end of the code, because during the code it will not run the MATLAB code, so that's why I have just defined the function in end of the code. So here is a plot for effect of device length. So it means almost 8 plots will come generate, and let me just wait, and we will get the output results accordingly. Okay. So here is a transmission of energy spectrum. This is just a second. Total density of states. These are the LDOS map. Local density of states, energy versus Fermi energy, energy resolved current, Fermi energy versus conductance, and the transmission of for different couplings, and the transmission versus device length. So if you need to ask anything, you just ask me. I will answer your questions. Thank you.